Then in 2012, I finished my PhD and did a bunch of startup roles and data science consulting roles. And in the last 4 years, I've been at Automatic, which is the company behind WordPress.com and a bunch of other companies. I helped put together, build our machine learning pipeline, which is mostly used for marketing campaigns. And now I'm working on our experimentation platform. And yeah, I have some online presence at yanirsarusi.com, which I don't often update, and on LinkedIn. And you can check out also data.blog, which is like the official blog of the Automatic data team. I think the most recent article there is for me. And yeah, also obviously plugging that we're fully distributed. It's like one of the biggest fully distributed companies in the world, and we're hiring for many roles, including on my team. So I assume you all have watched the talk, like the main lesson, which goes on for about 2 hours and covers a lot of bad stuff that can happen with machine learning. But to me, like the biggest takeaway from that is really, if you don't think about the context of your modeling or your modeling context, you're really going to have a bad time. So we'll break it down a bit. So what do I mean by think? It's really, we do know that machines can learn, but they're still not that great at thinking, and it's our role as the humans behind the machines to think about things that the machines don't know. And there are countless examples throughout history and today where evil consequences or bad consequences happen not because of some malicious intent, but just because of a failure to think. And what do I mean by the modeling context? So even if you just look at it from a purely technical perspective, there are many variations on this sort of figure that, like, anyone that goes and implements models in production sees, that like there is so much that needs to happen around your little machine learning model to actually have it work in production. And so that's like one part of the modeling context, but then there's the whole part of everything else in the world, including how it's used and inputs and stakeholder management and so on. So really the consequences of having this thoughtlessness and not thinking about your modeling context is, one, there could be some negative societal impact, as was covered very extensively in the lecture. But even if you don't care about society, you might care about yourself and how you're perceived. So it does happen that, like, if you don't think about what you're doing, you might be replaced by someone who does. Onwards. So, so like the lecture touched very briefly on like ethics as being the study of right versus wrong, and but obviously that's a pretty big question. So I thought I'd do like a very quick survey that's based on research into the foundations of morality, and we'll see how it goes with this online setup. Might completely flop, but to just touch on this question of what is good and what is bad, or what is evil and so on. So I will just, okay, I'll drop a link in the chat, and I'll also share a different tab. So there's this link in the chat that you can see on the side, and I will activate it. It's anonymous, so you can just skip the no, it's okay. It's anonymous, so you can just skip putting in your name. And I'll share the other tab and not raise my own hand. Yeah, so basically what we have here is two paired statements. And for each pair, the idea is that you select the one that you most agree with. I can probably full screen it as well. And oh, this is going nicely. I didn't know if it would completely flop or not, but the idea is that these questions are taken from surveys, like a much longer survey on the foundations of morality. And this is what what informs people's ideas of good and bad. So the first statement is about, no, I won't go through it as well, but yeah, no, it's cool to see the numbers changing. Yeah, so I will move right on from this. I had no idea how this will go. But the point is that we see that we don't agree on all these things. And indeed, I'll just go here. Share this. So this comes from research on the foundations of morality, and they found that you could one way that you could look at morality is to like split it into 5 different foundations of like respect for authority, care for others, care about fairness, loyalty to your in-groups like family or your country, and the feeling of purity versus disgust. And this slide shows that in the US and in similar countries, there's a pretty like sharp divide between left and right when it comes to the emphasis placed on these moral foundations. So on the far left, you have much less weight given to authority, respect for authority, loyalty to in-group, and purity, whereas on the right, all of these moral foundations play a role. And the whole, why am I saying this here is just because like, you know, whatever they say, like, and it's pretty implied in the lecture that there is like a very strong idea of right and wrong, but it's very hard to agree on a common set of ethics. So it's always good to keep it in mind. But with the question of good and evil all sorted, moving right along to some practical advice that goes beyond this course. So when I talk about thinking about your modeling context, one way to go about it is to really work on developing your critical thinking skills, or in more colloquial terms, work on your ability to call bullshit. So fortunately, there is this course from the University of Washington, and this is like a proper university course called Calling Bullshit, because bullshit is actually a well-defined term. And you can check it out on callingbullshit.org. And yeah, they've also put together a book on the topic that is definitely worth going through, because the way I see it, calling bullshit is really data literacy 101. So you have like the whole machine learning stuff that's about like technical side of building models, but if you're working with data, you need to go beyond this data literacy 101. But just to get the basics in, like it often starts with just asking a few questions, like these questions that they recommend when evaluating information, like who is telling me this, how do they know it, and what are they trying to sell me? So they have a few case studies on the Calling Bullshit website, and a few of them are pretty relevant to this course, so I thought we'd go quickly through one of these, and I was thinking of making it interactive in class. We can try to throw in answers or raise your hand in the chat. The original idea was to do it in class, but we'll see how it goes. So basically, this case study is on this paper that was published to Archive in 2016, titled Automated Inference on Criminality Using Face Images. So I'll read this snippet from the abstract. We study for the first time automated inference on criminality based solely on still face images. Via supervised machine learning, we build 4 classifiers: logistic regression, k-nearest neighbors, support vector machines, and convolutional neural nets, using facial images of 1,856 real persons controlled for race, gender, age, and facial expressions, nearly half of whom were convicted criminals for discriminating between criminals and non-criminals. So, any thoughts on what questions this brings to mind? It's very weird presenting to a muted audience, must say.
Feel free to unmute and talk, team.
Maybe raise your hand and then unmute yourself.
Yeah, like Sam says in the chat that there could be other cofactors like tattoos, and yeah, that's right. Like we will look into the data in the next step. They did account for it. Yeah, bias due to screen colors.
I would be fascinated to see on the convolutional neural net what the activation maps would show. I know that's not exactly the question, but that is the first thing that springs to mind.
Yeah. Yeah, so that it does go along these lines, and I'll go through like the data. So yeah, there is these questions of like what sort of biases. Like Joshua said, like biases in arrests and sampling biases. So yeah, we will see that these are the cases. So if we go to next slide, going deeper into the paper, so it really is like a question. These are the right questions. It's really what is the data, not what is the method. Yeah, and Ashley says that potentially incorrectly deem someone to be a criminal without any proof. So yeah, that's like the impact of these. Of what if it's successful? It's not 100% accurate. What happens if we deploy it? So yeah, if we look into like the description of the data, and this is like the core of it. So the data comes from, they collected 1,856 ID photos that satisfy the following criteria: Chinese, male, between the ages of 18 and 55, no facial hair, no facial scars or other markings, and they denote this data set by S. And S is divided into 2 subsets, SN and SC, for non-criminals and criminals respectively. Subset SN contains ID photos of 1,126 non-criminals that are acquired from the internet using the WebSpider tool. And subset SC contains ID photos of 730 criminals, of which 330 are published as wanted suspects, and the others are provided by a city police department in China. And these criminal face images are normal ID photos, but not police mugshots. So yeah, this does answer a few of the questions that the suggestions that people made. That yeah, there are like they try to control for cofactors like skin color and race because they're all Chinese and male, and tattoos. As Isaac says, seems like a regular dystopia to me. Yeah. But still, like, yeah, the criminals look more stressed out, that Huyen said is really, I think, even without seeing it, I don't know if you like read it before, but there is a bit of a subtle bias here, because like they are sort of like confusing in a way, because they call both subsets ID photos, but one of them is crawled from the internet, while the other one comes from actual ID photos. So they're not mugshots, but they are actual ID photos. And you would assume that one subset is musician. I was trying to read and think at the same time. So one subset is like supposedly would be more flattering photos that people select themselves, whereas, as we all know, I think many of us have photos that they're not particularly proud of in their IDs. Yeah, and Sam is pretty much spot on with like, are we building an ID photo detector? Because if you really wanted to compare photos of criminals to non-criminals, you would ideally take photos of them in the same setting. And yeah, there is the subtle issue of like, as someone said, that like there is a bias in sentencing. Yeah, lots of good messages in the chat. Yeah, so Jaco was also like, this is a more subtle thing where like the definition of crime is not the same across time or not the same across jurisdictions, and the level of evidence required to convict someone varies between place to place. So really what we are learning here is the biases in these data sets, and that don't generalize very well, as many people can say. So really, if the authors in the paper, they didn't supply the full data set, I think due to privacy reasons. So like half of them came from like, wanted ads that like are public. But if you look at this sample of the data with the free samples on top of criminals and free samples of non-criminals, what would you say are the differences that spring to mind? Yeah,
well,
exactly.
Non-criminals look a little happier.
Yep. Yeah, like they actually accounted for like the background and for the clothes. So like when they did the classification, they only took the face, so the sample doesn't show it, but they did remove the colors and all that stuff. But the top one, where you actually see the features, which I didn't include, that they do look happier, like a bit more relaxed, which is often the case, I think, when you have like a photo that you put of yourself on the internet that you want to look good, versus a photo that that gets taken of you. And they've used these eigen faces so this shows like after the cleanup. Here the criminals are on the left and the non-criminals are on the right, and this is more of an average photo. And we can see that even after you clean up the color and stuff, you do what you end up with is differences between facial expressions. So yeah, there may be false positives in like someone said, but really the whole premise of the paper is based on these like detecting actual differences between criminals and non-criminals. But it looks like what they built regardless of how good the results are, is something that compares smiley faces to not, or like, slight frown versus slight smile. So it is learning to detect the whatever collection biases exist. And yeah, so this is like the full study, or like the full paper is available on arXiv, and the full sort of case study is available on the Calling Bullshit website. And really, that at that point, like, you don't really care what they did as far as the machine learning goes. If you're working on a biased data set, it's garbage in, garbage out, and it doesn't matter. So like, they just called bullshit on the entire thing. And one last note on the topic of calling bullshit is that it's way easier to detect bullshit than to call it. Mostly because a lot of people don't like being criticized, or like don't like having their work criticized, especially when it's tied to things like identity or emotional, or things that they have like high emotional or financial investment in. But some level of calling bullshit or thoughtful dissent, which is a nicer term for it, is appreciated in many contexts. And well, I had this thought that it is sort of like deciding on your level of calling bullshit or thoughtful dissent is a bit like, much like tuning the learning rate of a model, where if you do it too much, you will antagonize a lot of people, you'll get shut down and possibly get fired. And there were a couple of recent cases with the people who work in AI ethics that got fired from Google. But on the other hand, if you don't ever call bullshit and don't ever say anything, then you'll get nothing done, and then you get all these outcomes of thoughtlessness. Getting it just right is easier said than done, but it does get you to an optimal point, but the terrain is very complex and largely unknown, as with machine learning. And yeah, that's another sort of big point, I think, from the lecture, is that this whole terrain of ethics is largely unknown. And they put this sentence like right at the beginning of the data ethics notebook, saying that because deep learning is such a powerful tool and can be used for so many things, it becomes particularly important that we consider the consequences of our choices. But this raises the question whether providing access to a powerful technology like deep learning with no controls on its uses is a good thing, a bad thing, or neutral. And who is responsible if a fast AI student goes out and uses what they learned here to harm people? And I don't have a very good answer for that, but I obviously don't think that it's all evil, because I wouldn't be here otherwise. But it's just an example to show that, yeah, it's a tough topic. But just because the questions are hard doesn't mean that we shouldn't raise them or think about them. And yeah, that's pretty much it for me. Happy to chat further on Discord. And yeah, remember to think about your modeling context as you move on to build models in the wild. And that's it.
Right. Yep. Okay.
Pass it on to Huyen.
Yep. Thank you, Anya. Yep.
No worries. I'll unshare my screen.
Can everyone hear me okay? Test.
Yep. I hear you before I mute.
Okay, good evening, class. Yeah, so I was preparing this lesson as an interactive in-person class. So I actually designed a few exercises for us at the end. So yeah, so with this class running virtual, it'll be interesting. But the silver lining is that now we have all these people joining online who have not been able to join in person, and it's a new experiment as well. So let's see how it goes. So this week, I'm going to continue to cover a few more theoretical concepts, continuing from last week. And I know that it has been a lot of material for you to go through in your own time, but I really believe that front-loading all of the theory from early on will help you make progress with your projects, and it will give you an intuition of what you are doing instead of just blindly copying the code. So to make this session interactive, I suggest that, when I ask the question, you can raise your hand. So there's a raise your hand button on your screen. If you want to answer the question, I can call on you, and you can unmute or answer the question. Or if you're too shy, then you can just type in the chat box. But yeah, I strongly encourage you to speak, to speak up, because it's a little bit eerie for me to speak to a mute audience. Yeah, okay, so let me start sharing my screen. Can everyone see my presentation? Yep, excellent, great.
Yeah, looks good.
Yep, so the key concepts that we are going to cover today are regularization by weight decay, data augmentation, the Softmax function, cross entropy loss, and we will end the class with a feedback survey from you. So if we recall from last week, towards the very end of Notebook 4, MNIST, Jeremy built a model using the ResNet 18 model to train on the MNIST data. And this is a very complex model, and it has 11 million weights. And Jeremy was able to achieve a very high accuracy within one epoch, one cycle of training. So if we train this model for 10 epochs, what can possibly go wrong?
Well, we could already get into overtraining if we're unlucky.
Yep, yeah, so correct. So with a model like this, so with this capacity of the model, so 11 parameters, you are very likely to overfit. And I know that this concept of overfitting has been covered in the past, but it's such an important concept that it's worth going through again. So can somebody remind the class what is overfitting? Yeah, Neil, can you speak up?
Overfitting is where the complexity of the model exceeds the complexity of the task. So it starts to fit to specifics of the data set itself and not generalities to the problem set.
Yeah, excellent. Sorry, let me just reshare so you can only see this tab here. Yeah, so correct. So basically, overfitting is when your model fits your training data really well. It's basically memorizing the training data, but for that reason, it doesn't generalize very well to unseen data. And the symptom of overfitting is when you examine the curves of the training loss and the validation loss. They start to diverge from each other. So as you train more and more epochs, your training loss continues to go down because the model is starting to memorize your data. Meanwhile, your validation loss starts to go up because the model is getting worse and worse at generalizing. And deep neural network can be very prone to overfitting. And why is that the case? Moji, can you speak up?
Yeah, because they're very complex and they have many parameters, so they have the capacity to learn the specifics of the data.
Yeah, exactly. So as we recall from last week with the MNIST data, so the dimension of your data is 28 by 28. So it's actually quite small. It's only over 700 dimensions. But when you have a model that has 11 million parameters to fit in the function, in the data, then you are very likely to overfit. And so the opposite of overfitting is underfitting, when your model basically just does not have enough capacity, does not have enough complexity to either fit your training or your validation data really well. So I learned by using analogies. So the way I think about these two concepts is underfitting is a little bit like the horoscopes. You make such vague and flexible predictions that sound quite vaguely true that anyone can relate to, but they also have very low predictive power to be useful. In contrast, overfitting, we can think of it as, say, Ptolemaic astronomy. So basically, it's a geocentric model of the solar system based on a very complicated set of nested circular orbits to explain the movements of the planets in our solar system. The problem with this model is that every time your new astronomical data came out, more and more circles need to be introduced in the model to explain the deviation, to explain the new data. And the model became so clunky that eventually people started to question the model, and they abandoned it in the end, and it was to replace with a much simpler model of Newtonian physics. And so yeah, I encourage you to come up with other analogies so that if you want to explain overfitting or underfitting to your grammar, you can do that, and we can come back to this point towards the end of the class if you come up with any good analogies. So one very common method to address overfitting is called regularization, and the common method is by weight decay. So basically what you do is you constrain the complexity of your model by ensuring that the weights of your model remain small. And you do that by penalizing the magnitudes of your weight. And you do that by adding this quadratic term in your loss function. So your new loss function is basically whatever your original loss function is plus regularization parameters times the sum of the squares of all your weights. So the larger your weights are, the higher this loss function is. So when you try to minimize the loss function, basically you want this term to be small, so you want the weights to be small. And in fast AI, this step is implemented really simply by adding this new parameter WD, weight decay, and then it will apply weight decay to your training. And I would like to present a probabilistic interpretation of weight decay to the more statistical minded people in the audience. And if you're not familiar with statistics, it's okay, don't freak out if you don't understand this slide. So if we recall from the last lesson, the cross entropy loss is the negative log likelihood of getting the data, right, of the correct class. So P of D given the weights and your input is basically the exponent of the minus of your loss function. You can think of the regularizer as the log of a Gaussian prior distribution over your weights. So that this is a prior distribution over the weights, which has this Gaussian form here. So if you multiply this likelihood function with this prior probability, then what you end up with is basically the posterior distribution over the weights. And if you are familiar with statistics, this is Bayes' theorem, right? And this posterior is equal or proportional to the exponent of the negative of your new loss function. So when we try to minimize our loss function, what we're trying to do is we're trying to maximize this term here, this posterior probability. And so we can think of these weights as the maximum a posteriori estimate of the weights. So you're trying to maximize this posterior probability of the weights given the data. So don't worry if you don't understand anything what I just said in the last 2 minutes, but yeah, if you are into statistics, then this is the interpretation. Another way to prevent overfitting is increasing your data points. And you can either do that by collecting more data, which is usually an expensive and a time-consuming process, or you can do that artificially by creating slightly different copies of your same data. So in the case of computer vision tasks, then basically you can flip, or you can rotate, or you can add some noise to your data. So just slightly different versions of the same images. So in fast AI, so Jeremy has found a set of augmentations that seem to work quite well, and it's captured in this transform here. And whereas if you want to basically create your own set of augmentations, you can do that as well by specifying these different arguments under the transform function. So in this example, you will flip your images during training. You flip it vertically. You rotate the images by 10 degrees maximum. You can zoom in the images as well, so on and so forth. What can possibly go wrong with data augmentation? What do we have to be careful about? Bryce, can you answer this question?
Yeah, so the augmentation has to make sense for what you're doing. For example, if you're doing street signs and you're augmenting a no left turn sign, and you flip it, you've got yourself a no right turn sign, and that might not be what you want.
Yes, very funny. Yeah, very funny example. Yeah, that's exactly right. So not all augmentations might be applicable to your problem. So you have to be careful. So for example, say this task is you're trying to classify images of lemon versus lime. So if you want to augment the data by changing the hues of your images, that would be nonsensical, right? So, or sometimes when you distort your data so much that it no longer makes sense, like when you can no longer recognize the cat, then you're effectively adding noise into your data. You're stripping away the signal in the images, and you're adding noise, and that can actually make your model worse instead of making it any better. And you have to be especially careful when you deal with a new data domain. So say medical images or geological scans, they are very different from natural images. So certain transformations might not make sense to them. When you distort the images, you might actually completely lose the information in your images. So the augmentations have to make sense to your data. So other methods to address overfitting include L1 regularization. So the previous method, weight decay, that I mentioned is called L2 regularization, and L1 is a different one. Or drop out. So basically, you randomly you randomly drop out some of your weights during the training. Or early stopping. Basically, you stop before your training loss and your validation loss diverge too much from each other. And if you're interested in understanding these concepts a bit more, you can discuss with us after class. Now, jumping on to a completely unrelated topic, I'm going to cover the Softmax function. So if we recall from the previous lesson, so we had a binary classification task of whether this image is number 3 or number 7, cat or dog. And we use the sigmoid function to turn our output into a probability, right? But when you have more than 2 classes, so in the pet breeds example, you have 37 different breeds of dog, then you need to have a different function to turn the output of your model into the probabilities. And that function is called the Submax function. So basically, you have your input that goes through the model, and it will output the number of classes. So in this toy example, you have 5 raw outputs, and you will run them through this Softmax function here. So you take the exponent, and then you divide it by the sum of all the exponents, and that will give you the probability of the different classes. And then you also have the true label for that particular example, which is 1 for the true class and 0 for all the other ones. And from your probabilities and the true label, the loss function is minus the sum of the target times the log of your probability. So in this case, it will be negative log of 0.09 because 0.09 is the probability of the true class, right? So when we want to minimize the loss function, really what we want to do is we want to make this probability as close to 1 as possible, right? We want to get the probability of the true class to be close to 1. And the binary cross entropy that we discussed last week really is just a special case of the cross entropy for the binary case. So you have your input, and which gives you, and it goes through your model, and it will output one number. You take it through the sigmoid, and you will end up with 2 probabilities for the 2 classes. And then if you plug that into the formula of the cross entropy loss, then yeah, you end up with the formula that we had last week. So really the binary cross entropy is just a special case where you sum over 2 classes instead of 5 or 37. So now we are going to do a couple of exercises, and initially the idea was to divide the in-person class into 2 teams, and one team will answer this question with pen and paper, and the other will try to find the solution through code. But now I think we're just gonna go through them one by one and as a whole class together. So if we recall from the last class that we built a really simple model from last week, one linear layer ReLU and another linear layer. So let's maybe ignore this question here. If your first layer has 30 nodes, if your linear layer has 30 nodes, how many weights does your model have? You can type in the answer in the chat box, or you can raise your hand. Remember that the dimension of your input is 28 by 28, so 784 dimensions. Michelle, can you explain your answer? Why is it 1,628? No one has got the right answer yet. Michael Senesco, can you explain why you have 23,520? You have 10 categories. Yep. Someone has got fairly close to the right answer, but it's still not right, quite true. Yeah, okay. So one linear layer, ReLU, and another linear layer. So remember the dimensions. The dimension of your input is 784, and the output is 10. Someone has got fairly close to the answer, but still no one has got the right answer yet. Nope. Nick Marsh has got very close, but still not quite true. Yep, remember we have the bias term. So maybe let me go back to that to remind you what the formula looks like. Michael has raised a hand. Can you answer, Michael Sinesco? Yeah, so remember that our simple net looks like this, right? Yes, okay, finally we got the right answer. Okay, Nick Marsh, can you explain how you got your answer? Can you unmute yourself, Nick?
Yep. So input dimensionality 28 by 28, multiply them by the nodes on the input. So multiply that by 30, and then add another 30 for the biases. That's the first layer, and then the second layer is the input from the first layer, which is 30 times 10 categories plus 30 biases.
Yep. Okay. So I made a mistake as well. Yep, you're correct. Yep. Sorry, I just typed in the correct answer. So remember, in your first layer, right, your input is 28 times 28, and you have 30 nodes. So 28 by times 28 times 30, and then you also have the 30 bias terms, right? And then your value doesn't have any weights. And then in the second linear layer, you have 30. The input is 30, and the output is 10, and then you have the 10 bias terms. So if you add all these things together, I think you end up with 23,860 parameters. Yep. Cool. Okay, let's go back to that. Can people still see my screen? Looks like I have lost it. Nope. Okay. Yep. Okay. If the batch size is 100, what is the size of your output? This is the easy question. Yeah, okay, so Fahad has got the right answer. So you have your batch or yarn sobers. Yeah, so you have your output is 10, right? Because you have 10 different classes, and your batch size is 100. So the dimension should be 110. Cool. If we think about this model, can you think of what might be the disadvantages of using this model? Remember that the simple net has this architecture here. Anyone else wants to raise their hand apart from Neil? Amit, can you speak up?
Yeah, I think so. Based on the theory in the videos, because it's just a two-layer network, we may need a lot of parameters to train it properly, or a lot of weights to train it properly.
Yep, that's correct. Yep.
Okay, cool. Thanks.
There might be something else. Can someone, Neil, do you want to offer a different answer?
So the network we're using here is a fully connected set of dense layers, which can memorize position of each pixel, but it doesn't look at pixels relative to each other's position. So if you were to take images that were slightly offset, it wouldn't be able to understand them.
Yes, that's exactly right. So if you imagine that your image is shifted by 1 pixel, right? And when you flatten this image into one single row of 784 numbers, it is a completely different vector, right? But in reality, the relative positions of the pixels have not really changed apart from that shift. And so basically the problem with a model like this is that it has completely lost the spatial information in your images. And that's why when we have computer vision, tasks, we have the convolutional neural network, because the convolutional part deals with that. It preserves the spatial invariance of your images. Does anyone else want to offer another answer to this question? Nope. Okay, great. We move on to the next question. Okay, so we have a ResNet 18 model trained on the MNIST data. And in here, I have generated 3 basically, learning curves using the learning rate find function that we learned from last week. So basically we feed, one batch at a time, and we see how the loss function changes over time. And these 3 plots use 3 different batch sizes, 16, 64, and 512. Can you tell which plot corresponds to which batch size, and explain your reasoning?
So I just naively say the smoother one's the larger batch size. That's just as you're kind of getting away from being less stochastic.
Josh, yeah, that's great. Yep, that's exactly correct. So if we remember from last week, right? We remember from last week when we do stochastic gradient descent, we take the derivative of the loss function with the weight, relative to the weights, with respect to all the weights. And I mentioned that, ideally we want to calculate this gradient using all of the data, and that will give us the true gradient, but that will take way too much time. So we only feed it a batch at a time, and we use that gradient as an approximation of the true gradient. So the higher your batch size, the smoother, the better the estimate should be. Whereas if you have a small batch size, that can be, that estimation can be really noisy. And that's exactly why, when you have a smaller batch size, the loss function is a bit noisier. Whereas when you increase the batch size, you can see that the loss function becomes a lot smoother. The next question is a higher batch size generally a good thing? And think of the loss function landscape that we discussed last week. Think about this image here. This is how bumpy and how complicated and chaotic your loss function might be. Is a higher batch size necessarily a good thing? Yep, great. So Sam has got the right answer. So the benefit of having a smaller batch size, a larger batch size, is that you have a better estimate of the gradient. But the problem is when you have a complicated, a chaotic or complex landscape like that, you might actually be stuck in one of the local minima. Whereas if you have a small batch size, your gradient estimate is noisy, but sometimes noise is actually really beneficial in this case, because sometimes you go in the wrong direction and you might end up somewhere better than where you are. That's great. So I will share this notebook with you, which demonstrates this point in the chat. And you do not need to run the notebook again. You can just view it. And maybe we spend maybe 3 minutes looking at at the notebook, and then you can share, what have you found by looking at the results. Yep. So I have posted the link to the notebook in the chat. Yep. Yeah, so we spent a couple of minutes looking at the notebook. You don't need to run it. You can just view the results, and you can feel free to make some observations about what do you think about the results. Amit, do you still want to make a comment, or is it from the previous question?
Yeah, it's from the previous one. Sorry.
Yeah. So when you look at the notebook, what have you noticed? Yeah, so I think we've got 3 comments here that are all correct. So you can see that the larger batch size at the bottom never actually achieves the same accuracy as the previous 2. So it seems to struggle a little bit. So it looks like it has been trapped in a local minimum. And also, if you look at the first 2 scenarios, there seems to be some level of overfitting. So it seems like it starts to overfit around the 4th epoch. Would you say that batch size 16 is better, or 64? It seems to me that they are fairly similar in terms of performance. Yep, great. Okay, now we will move on to the last exercise. What happens when you use a massively high weight decay parameter? Amit, do you want to take this question?
So will the model be more underfitted because it will, the higher weight will try to restrict more learning? Like it will be underfitted, I think.
Yes, yeah. So recall why we do weight decay in the first place. We want to reduce the capacity of the model, right? But when we use a massively high weight decay, then we can go a bit too far, and we reduce the capacity so much that your model no longer has enough flexibility to learn from the data. And actually, sorry to go back to the previous exercise. Actually, I never actually had enough time to do this experiment on a different data set, but I'll be quite interested in what happens, if we do this on ImageNet. So if you have the time, experiment this, try different batch sizes and see, whether it's true that, higher batch size is bad. Because it seems to me that this is still a fairly open-ended question in research. So yeah, so we can experiment and find out, because I don't know what the answer is. Yep, so now I'm going to share with you the notebook for exercise 3. So exercise 3 again has been run, so you do not need to rerun it. You can just look at the results. and you can make observations about what happens when we increase the weight decay parameter. Cool. So what do you observe in this exercise? Okay. Notebook loading error. Interesting. The weight decay overpowers the true weight. Stephen, can you explain what do you mean by that? Stephen, can you unmute yourself? And
if I'm not mistaken, it's like the actual weight that we have in the previous iteration is actually because of the weight decay. It's the model is not confident enough to put out its actual weight. Instead, because of the weight decay overpowering the true weight, the actual weight that is learned by the model.
does anyone want to respond to that? I'm not entirely sure I understand your answer. So yeah, so Neil made an interesting comment here that, you know, there's no consistent rule as to what the ideal batch size should be, and I kind of agree. It seems to be an experimental thing and highly dependent on your data set and your model. Larger weight decay brings losses close to each other. Mohammed, can you explain what you mean by that? Mohammed, can you unmute yourself?
Yeah, so when we do a weight decay, so some of the activations would be ignored, which actually decreases overfitting of the model, which in other case would bring our validation and training losses together. So
Okay. Yeah, so I think if we go back to the loss function when we use, and also like the last graph is quite interesting, that something weird seems to happen here. Not exactly sure what's happening. It seems like it jumped out of a local minimum and then it starts to go downhill. It starts to do the gradient descent again. And actually, just out of curiosity, can somebody explain to me what is this x-axis here? Why does it have 3,000, about 3,700? What is it actually plotting? So it's plotting the training and the validation losses against something. But what is this x-axis? So remember that our batch size is 128, and we are training it for 10 epochs. So what are these numbers on the x-axis? The number of epochs times batch size. No, not quite. Because the number of epochs is 10, right? And the batch size is 128. So that's not quite correct. Epochs, nope, the number of epochs is 10. Jan Sobus says batches. Can you explain what you mean by that? Can you unmute yourself?
Yeah, so I believe it's, I don't know how large the dataset is, but it seems that it just counts every batch it's trained for. So it's the total number of batches in all the iterations.
Yes, yeah. So it's the number of iteration. So Stephen has got the right answer here. So it's basically the total number of data points divided by batch size times the epochs.
Yeah.
So yep. So remember that our MNIST data is 60,000 samples, and we keep 20% for validation. So we have 48,000 samples for the training, right? 48,000. And then the batch size is 128. So 48,000 divided by 128. That's the number of iterations in each epoch. And then you train it for 10 epochs. So you times 10. And that will give you 3,700 iterations. So that's the number of times that you go through, batches. Yep, that's great. So that's all for this week. I hope that you have found the exercises useful and given you a bit more understanding of the training. And now I'll pass it back to Michael to go through the class survey, because we would love to hear some feedback from you, and and help us improve how to run this course as well. Thank you.
Sure, thanks, Wen. I will pull up some of the findings from the survey. Bear with me. Where are we? Sorry, Google Chrome isn't showing up in my. Give me one more go. So thank you for those who have already filled it out. That's not the one that I want. It's a little bit more challenging. All right. So I'm struggling to get this on the screen. So what I'm going to do instead is just go through some of these numbers with you guys. So actually, let me share my screen. That works better. Okay, perfect. There we go. Okay, sorry. So just going through some of the responses now. We've had 10 responses. Please make sure to fill this out if you've, if you haven't already. First one was just to get a bit of a feel for everyone's experience. I may go through a little bit later and see how the responses differ based on the groups. Overall, good to see that the recap slides are interesting and useful. A couple of things that I noted was that a couple of people liked when it sort of builds on the actual course content rather than just regurgitating what was in there, which is definitely something that we're focusing on doing. The coding, live coding had sort of mixed reviews. I think when we're sort of going through from scratch, it can be a little bit slow. There's also an answer in a later question about that. having those set up so that they can be run from top to bottom a bit more easily seemed to be something that someone said. The responses for the live coding.
Sorry, Michael, can you make the screen a bit larger so that we can read the content?
I can. Sorry. How can we make the course recap slides better? So live coding, so a little bit more mixed, but still, you know, generally positive. Live coding sessions could be made better by providing them a little bit further ahead of time. Yeah, a few other bits and pieces here. I'll have to go through these a little bit more. But following on in person, one comment said following along in person was a little bit distracting. So potentially, yeah, just organizing those a little bit better potentially. So next one was on which sort of activities you guys into. First one was obviously, yeah, generally lots of likes, shares and subscriptions for the content recap slides with interactive Q&A, which is great. The weekly lesson questionnaire was fairly mixed, so it's something that you guys can sort of do on your own or do in your groups, which you can potentially go do very soon. Next one was going through the mentor notebook with or without live coding. Generally, people preferred going through with live coding, which is good. I think as long as we obviously get that right. Next one was group project work. Again, mostly positive. A couple of dislikes here. Potentially, it could be because that's taking time away from, you know, time with mentors. Feel free to share any thoughts on that as we go through this. And then very positive for other presentations beyond what's in the course. The final question here on that note, if the mentors were to prepare presentations on other topics not covered in the course, not to the course, what would you like to hear about? The overwhelming two here are about how machine learning is deployed in production in industry and preparing to get your first job in machine learning. There's one answer here on study groups from, project presentations from each of the teams. We will be doing that later on in the course. I guess it's a question whether we do that earlier as well. And then someone else who's answered on skills and CV advice, ML in industry. Well, it sounds like they just want many things. Not sure we can do all of those, but definitely some, yeah, fair bit on what ML in industry looks like. And then I guess pathways into jobs, whether it be via PhD or skills and CV advice. Potentially we can loop that into a sort of preparing to get your first job in machine learning talk. Yeah, overall, I think it aligns fairly well with what we found so far. So I think in the next couple of weeks, we'll look to do particularly these two topics, probably one on each. What it looks like in production, both how models are deployed, but also just what do a lot of the projects look like. What could you expect if you were to drop into a role either in a machine learning consulting business or a product business or something else, or research potentially, and then also, you know, what can and should you do in order to make yourself as attractive as possible to potential employers. So I think we'll look to put those together this week and slot them in the coming weeks. But yeah, any other thoughts from anyone else?
Speak up if you want to give us any direct feedback.
Otherwise, feel free to just fill this out and add any comments at the end there. I'm not going to go through in the comments because obviously you guys have submitted those directly. But yeah, overall, I think the key thing for us is obviously the recap slides are good. I think they've been pretty good so far. We will avoid the weekly lesson questionnaire is still positive. I think we just do more of the same. I think the main thing for us is just maybe throwing in a couple extra presentations in these next couple of weeks. Yeah, sounds good to me.
Yep, Ellie, do you want to speak up? Do you want to unmute yourself and speak up?
Yeah, so I wanted to make a comment regarding the recruitment. I've participated in a couple of interviews, but what I found was there is a tendency of focusing on data analysis and statistics. And looking at the content that we have here, it looks like we overlook data analytics, but when you go to the interview, you are mostly likely to be asked questions related to data analysis. So what's your take on this, and what are you planning about it?
Yeah, so I suppose this course is definitely a machine learning course, right? It's very much focused on building models, and even within that, it's very much focused on deep learning with fast AI. Whereas what you'll find, and you might have found, is it Eli or Ellie? I'm not sure.
Ellie.
Ellie, perfect. You obviously work in a data engineering role, Ellie, as we talked about before, I believe. But what you'll find is that a lot of roles in industry are still analytics or data science focused, particularly at big businesses. So, big banks and financial services and big retail companies like that. What you find is that these days they might put machine learning in the job descriptions, but in reality, they've essentially just rebranded their analytics team to now be data science and machine learning. And you don't actually do much machine learning. You actually just do a lot of BI and stuff like that, a bit of data science, maybe some stats. So look, it does really depend on the jobs you go for. I suppose some of the advice that we'll probably talk about in the preparing to get your first job in machine learning is really, how to choose the right roles to interview for, because if the majority of a job description doesn't actually talk about machine learning, it's probably not machine learning. It's probably data science and, whatever that entails, particularly if they're talking a lot about BI tools or data pipelines. So yeah, there's obviously a lot less pure machine learning roles in industry than there are general analytics. A lot of businesses aren't doing a lot of machine learning at this stage. So I guess what we might try and work into that talk is also a little bit on how do you identify the right roles. And given that there aren't as many out there, how can you set yourself apart from people who might be data scientists who do a bit of ML, a bit of data, a bit of engineering, et cetera, et cetera.
Yeah, I just want to add a comment to Michael's response that, this field is vast, right? We have so much material that we want to cover, and it's mostly based on fast AI, but we are aware that we haven't really covered that much actual fast AI material much, and there's still all this background behind the scene as well. So it's always a difficult balancing act, like how much should we cover, and also the coding aspect of it as well. So it's really hard, but yeah, in the future, I guess we will try to incorporate some of that more general knowledge in our future lessons.
And obviously, it's a single course. It's focused on deep learning with fast AI. There's other courses that you could do, maybe not in the same vein as this one, but definitely there's a lot of courses online or different learning platforms. Rather than trying to cover too many topics in what is a relatively short course, we'll really try and focus on using fast AI and try and refer you guys to some of the other places that you can go to learn those complementary skills. So expect some stuff in that talk on getting a job in machine learning and sort of what to look out for and what skills to build. We'll try and drop some resources and some places to look to help you with that.
Does anyone else want to raise any other comments?
Cool. While we're here, so it is 7:20. Oh, sorry. Go for it. Did we have someone else who wanted to talk there?
No, I think maybe that was a mistake.
No worries. Yeah, so it is 7:25 now in Brisbane time, so we've got another 35 minutes for the session. I think at this stage, that's probably all we have from the mentors ourselves. So there's a couple of things that I would like to just mention before we let you guys go. So obviously there's a little bit more time to go. I've set up a few more channels in Discord, some basically study lounge channels. I can create a few more as well, but right now there's sort of 6 of them. what we might do is if you guys want to get together in your groups, feel free to hop into some of those with your group. Alternatively, if you do want to catch up in some of your sort of private channels, definitely do that and catch up and see how you're all going. On the topic of group projects, we are 2 or 3 weeks in now that you guys should be making progress. So I hope that a lot of you are making some good solid progress. You're at the point where you're building models and starting to tune those. I definitely encourage you guys to make sure that you make more of your progress earlier than leaving it till later, because challenges will come up that will need solving. So please make sure that you're focusing on that and setting enough time aside. One thing that I did notice in one of the responses from the feedback form was, someone had had a bad experience where they'd started with a few team members, extra people had outed themselves, and then they'd also just dropped off. So if you are contributing as part of a team, please make sure that you continue working with your teammates. If you do need to disappear, please just communicate. If you're not going to be continuing, at least let them know so that if they do need to merge with another team or something else, they can do that. The only other thing, and I might also put my camera on for you, maybe not, doesn't want to work. The only other thing I would say is, as you guys are working on things, make sure that you are, a few people have been talking about blogging and writing blog posts about what they're doing. I think that's a fantastic idea. Definitely encourage. Jeremy really encourages it as well. Just make sure that when you are doing those, you're making sure that you're producing original content. There's a few different groups working on the same data sets. If you are, checking out what other teams are doing, make sure you're, giving attribution. Likewise, if you're writing blog posts and referring to papers or other blog posts on the internet, make sure that you're giving attributions to those that have sort of, helped you along the way or things that you reference. The beauty of the sort of software world and particularly machine learning in the last few years is that everyone loves to share. It helps us all, learn and grow and get things for free, hence fast AI. So if you are going to lean on the shoulders of other giants and, use some of their work, make sure that you attribute where you've borrowed, which is good as well. But that's all from me. Anything else to cover, other mentors?
Do you want people to start presenting the progress on the project next week, or do we leave it to a later date?
Potentially. I think the main thing will be just, I think if we want to get 2 of these talks in, I think we might have one talk left to go. While we're on the topic, we might even just talk about it a little bit. I've had a chat to a couple of the people in the in-person course about how we, as we do get to the end, how are we going to do the judging and, make sure that we're choosing the right winners and everyone can show off their work. At this stage, we do have a lot of different teams who are presenting work. So rather than having a 5-hour mammoth session where every team presents their work, some of those may not be fully developed, others might be really well developed and deserve a bit more time. What we may look to do is actually sort of have people sort of present their work, maybe record a little video or do a slide deck with a demo. Potentially all of us may then vote on, which ones we think are, the best and deserve to be seen by everyone. And then when it comes to judging at the end, it might be the case that we select the 10 best and then those get presented to judges. So trying to have a think about this. If you have any ideas about how that could be better, please let us know. But that's probably the thoughts right now for how things look at the end. It might be the case that we also do a little bit of a session beforehand. It'll just be a matter of slotting that in. And obviously you guys need a little bit of time to prepare as well. But I think one of the key takeaways there is it would be awesome to see, if you guys want to do some presentations of what you found so far, if you do have any demos, that'd be fantastic. Maybe just, just drop something in one of the main channels, just tagging the mentors and saying, your group would love to share something. We can then go and chat to you in your Discord channel and hear, what you'd like to present, what you've got ready to go. That might be the best way to do it potentially. But yeah.
Yeah, we don't expect like a full or complete presentation at this stage. So if you can share, you know, a lesson learned, you know, something you have, an obstacle that you have overcome when using the Fast AI library, or a roadblock that you're running into that you need help with, I think everything will be, you know, very beneficial to your classmates to learn from. Yeah. So yeah, don't stress too much about, you know, the presentation at this stage. It doesn't have to be complete. Yeah.
And it could be a 2 or 3 minute thing. It doesn't need to be big either. It's a work in progress, right? So yeah.
Great.
Awesome. All right, guys. I think at this stage, we'll let you go. We will start working on some of the other things that you guys have shared with us in the feedback form. Again, if you haven't submitted anything, please do. And we'll leave you guys to go. I will make a few more channels in the Discord, some extra voice channels, given that everyone's online. That way you can chat and hear each other's lovely, beautiful voices. And yeah, we'll end the video call here. Hopefully we'll see some of you in person next week. I'm curious to see what the likelihood will be over the next couple of days, but either way, oh, how many active projects do we have? There you go, 41 groups, that's a lot. Hopefully we see some of you in person in next week. If we don't, we'll be here again. So yeah, chat soon, guys. Have a great week. Thanks again. All right, ciao.